Hello everyone, I am Yu-Sheng from Inventec Corporation. Today, I will introduce you a dense Tensor Accelerator architecture that optimizes the memory utilization in deep learning. Memory bandwidth has become the most critical problem in deep learning computation. This is because people tend to use deeper networks and smaller kernels. As a result, the red part in this figure, which is the memory accessing power, occupies more than 80% in deep learning computation nowadays. To reduce the memory power, we know that the memory characteristic is determined by the tile size of an architecture. For example, a TPU uses a large 2D PE array, and the PEs share a large global buffer. The resulting architecture is area efficient, but it also uses a lot of memory bandwidth. Iris broadcasts the data from global buffer to the local buffer, so a PE can process a small tile without accessing global buffer. This reduces the global buffer bandwidth, but causes data duplication across different PEs. In a vector processor like GPUs, a small number of local buffer and PEs form into a group. Within a group, the PEs and the local buffers are connected with a more powerful interconnection. This avoids the data duplication within the group. However, the data sharing across different PE groups is still not trivial. To minimize the global buffer bandwidth and avoid the data duplication across the buffers, we propose the VectorMesh architecture. The basic unit of this architecture is the Tile Execution Unit, or the TEU. A TEU consists of several PEs and local buffers, which is similar to the vector processor. The neighboring TEUs are joined with a small FIFO, such that the TEUs forms a 2D mesh. This figure shows the internal of the TEU. It has a SIMD of 32 PEs and a partial sum buffer. The below are two input buffers, and each input buffer consists of 32 local buffers that is routed to the SIMD through a butterfly network. Other than the VectorMesh architecture, we also propose a scheduling methodology to maximize the memory efficiency in VectorMesh. Specifically, if we want to share the data through the FIFOs, we must ensure that the workloads are scheduled at the correct time and put on the correct TEUs. We take a block matrix multiplication as an example. In this example, 4 TEUs process the submatrix PQRS independently, and each TEUs also require 4 submatrix to complete its works. This figure shows a possible scheduling for this example. In the first time phase, matrix P and Q compute the matrix multiplication EW and EX respectively, so we only need to fetch matrix E once. And similarly, matrix P and matrix R only need to fetch the matrix W once at the first time phase. This method not only works for matrix multiplication, it also works for CNN. Moreover, it works for modern networks like the correlation layer, or even the traditional workloads like the motion estimation. Please refer to our paper for more details. We use the roofline model to show the efficiency of our architecture. For MobileNet, FlowNet, ESPCN, or the display, our VectorMesh architecture can reach the upper bound of the roofline. Compare VectorMesh with state-of-the-art architectures. Our architecture is the closest to the roofline for standard CNN workloads. Even consider that TPU has a smaller area. This means VectorMesh has the same normalized performance when compared to the other architectures. At the same time, it can save up to 22 times global memory bandwidth and 5 times DRAM bandwidth